Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about multivariate continuous random variables. The goal is to learn how to model the interactions between multiple continuous quantities that are uncertain. The prerequisites for this material are multivariate calculus, including partial derivatives and multivariate integrals, and also multivariate discrete random variables. Let us remind ourselves what the mathematical definition of a continuous random variable is. A continuous random variable is a function from a certain sample space to the reals, maybe I'll change the color, such that the probability that we end up mapped to an interval is well defined. Okay, so maybe I'll draw a little picture. The idea is that we have a sample space omega, and the random variable maps points of omega to the real line. To the real line in a way that the probability that you end up in a certain interval, maybe I'll draw the interval in black, the probability that you end up in a certain interval, that's the probability of all the points that map to that interval. Okay, all the points such that if we're calling the random variable A, such that A maps those points into the interval, that probability, if that probability is well defined for every possible interval, then we have a valid continuous random variable. If you want to be fancy, that's called a measurable function. Why is it called measurable? Because the probability measure of the probability space gives a probability to any such sets that then map to any such events that then map to an interval. Because of the properties of probability spaces, and in particular the properties of the collection of events within a probability space, that means that any event mapping to a union, an intersection, or a complement of intervals is also going to be in the original collection. There's also going to be a probability assigned to it. Okay, and those sets have a fancy name, which are called Borel sets. So that's how we define a continuous random variable mathematically. Of course, we very quickly forgot about this and then defined the CDF and densities and just worked with that. And we're going to do something similar for multiple random variables, but first we have to make sure that we understand the mathematical framework underlying everything. So that's why we're talking about probability spaces to start with. But then later on we will forget them as usual. Okay, so what happens if we have two continuous random variables in a probability space? Then if we consider two sets A and B, which are Borel sets, so basically countable unions of intervals, or two intervals, or the intersection of two intervals, etc., then the probability that each random variable is separately maps to those intervals is well defined. Because of that, we can actually define the probability that a certain outcome is mapped to both intervals. Okay, like formally that means that if we build a vector where the first entry is the value of the first random variable and the second entry is the value of the second random variable, then we can consider the event that that vector ends up in the Cartesian product of A and B. So let me show you what this means with a very simple picture, because the notation can be quite confusing if it's the first time that you come across it. Okay, so the important thing here is that we're going to consider random variables that are defined in the same probability space. Same probability space, okay? The probability space is this one. Okay, and it's called omega. And now we have a random variable A that maps points in omega. So let's draw a point here, for example. It maps points in omega to the real line. Okay, that's what A does. It's a valid random variable. It maps 2 points in the real line so that the intervals have a well-defined probability. Okay, so that's A. But we also have B that is also defined on the same probability space. It also maps points onto the real line. Okay, so we have this real line here. I'm going to draw another real line to represent, maybe I'll draw it as a straight line, to represent, points to show where B maps points. Okay, so B would map this guy maybe here. So now, if we consider this vector here that we have here, where the first coordinate is where A maps to, and the second coordinate is where B maps to, this gives us like a multivariate function basically, where this guy here ends up mapped to a 2D point, where again the first coordinate is the value of A, the second coordinate is the value that B maps to. Okay, the value that A maps to is the first coordinate, the value that B maps to is the second coordinate. So now we can ask, what is the probability that this mapping, this 2D mapping here, ends up in a certain rectangle? Okay, so let me maybe clean this up a bit. What's the probability that we are in a certain rectangle here? A rectangle is just the Cartesian product of two intervals. Okay, that A, in order to be inside that rectangle, A has to be in this interval and B has to be in this interval. So now we can think about, okay, in the original sample space, what are the points that map to this interval here? Well, maybe they are these points, let's say. And we can also think about the points that map to this interval here, okay, through B. And maybe those are these points. Now, the points that end up in the rectangle, in the black rectangle there, those are the points that are mapped through A to that particular interval, and at the same time also through B to that other interval. So they're exactly this intersection. Now, the red event in the sample space is well defined because it's the points that get mapped to an interval by A, and A is a valid random variable. The green event is well defined because B is a valid random variable, and those are all the points that are mapped to an interval by B. So their intersection has to be well defined by the properties of the collections in probability spaces, which is awesome because now this 2D vector that we have can be basically has a well-defined probability of being within a rectangle, and by the same argument, it has a well-defined probability of being in any union of rectangles, intersection of rectangles, complement of rectangles, and so on and so forth. Just because A and B are valid continuous random variables and they're defined on the same probability space. And that's essentially how we define the joint distribution of multiple random variables mathematically, okay, by making them share the same underlying probability space. Okay, so now this intersection of the red event and the green event is well defined, so this guy is well defined. It must have a probability assigned in the original probability space. I'm not going to draw this because I can barely draw in 2D, but we can do exactly the same thing for the different random variables that we can stack up as entries of a vector and call that a random vector. If they're defined on the same probability space, then we can consider the event that the first entry is in a certain Borel set X1. Remember, Borel set, just a fancy name for countable union, intersection, complement of intervals. That's a bit long to say every time, so we just say Borel set, and then we sound a bit fancier mathematically. So we have these Borel sets X1, X2, XD. We can consider the event that each entry is in each one of these Borel sets, so you're within a hyper rectangle if the Borel sets are intervals, or you're in a union, intersection, etc. of hyper rectangles. We're just multidimensional generalizations of the rectangle that we drew back here. Okay, this rectangle there. So that's great, because essentially this means that if we have some valid continuous random variables that are defined on the same probability space, we can immediately think of their joint distribution in this d-dimensional space, and it's going to be well defined as long as we consider these reasonable sets that are rectangles in 2D or hyper rectangles, or unions, intersections, and complements of hyper rectangles. As in the case of 1D, it could be that you could, there exists some very contrived sets that can be built which cannot be expressed as a countable union of hyper rectangles, but you will never encounter them unless you go study hardcore measure theory. And if you're interested in that, I encourage you to go look into measure theory. It's a very cool subject. Okay, so I got a bit excited, a bit carried away there. The point is that if each of the entries here is a valid continuous random variable, then the probability that you're in this Cartesian product of Borel sets is well defined. So we're good. As in the case of single random variables, we're never going to construct this probability space explicitly, because that, it's just not even tractable if we tried in most cases. It doesn't make any sense, because at the end, what we really want to do is think of these multiple random variables or this random vector as an uncertain quantity, and we want to quantify directly the probability that that quantity is in a particular region of the d-dimensional space. And the way we achieve that is by defining the cumulative distribution function and later on the density. But these rely on the underlying probability space, so mathematically we still need to know that there's a probability space defined there, although we will never build it explicitly. I hope that makes sense. Okay, so in the case of one single random variable, the cumulative distribution function is just the probability that the random variable is smaller than any specific value for all possible real values. Okay, that defines a function, and that actually describes completely the random behavior, the probabilistic behavior of the random variable. In the case of two random variables, the joint CDF is defined in a very similar way. The joint CDF at 2 points, or at a two-dimensional point, maybe that's easier to, maybe we should say it that way, is just the probability that the first coordinate is more or equal to the first coordinate of the point, second coordinate of the random vector is more or equal to the second coordinate. So maybe we can just draw a picture. Imagine that we have A and B. I'll draw them in the same color now. A and B. So maybe A0 and B0 are here. The value of the CDF at this point, f of A0, B0, is the probability that the 2D random vector ends up here, where, this goes to minus infinity. This is the direct generalization of the 1D CDF, 1D cumulative distribution function, where it was the probability that you were to the left or something, smaller than something. Okay? Exactly the same thing. In the case of d-dimensional random vectors, we define the joint CDF at a certain point as the probability that the random vector, the entries of the random vector, are smaller or equal to the entries of that point. So same thing. Let's take a look at the properties of the joint CDF. So again, I was going to go back to the picture, but I'll just draw it again. So we have that the CDF at a certain point here is the probability that we are in this region here. in this region here. So now what happens if we take one of the coordinates and we move it to minus infinity? This is the same as what happened when in the univariate CDF we considered what happens when we take the argument to minus infinity. So f of minus infinity, or something that tends to minus infinity for the univariate CDF, we saw that was equal to 0, because if you fix the random variable by making the point arbitrarily small, eventually the probability that you are smaller than that has to be 0. So here, same thing. If we fix the random vector and then we say, oh, what's the probability that you're smaller than that the first coordinate, in this case, is smaller than an arbitrarily small number, eventually that's just going to be 0. Same thing for the second coordinate, of course. And now you can think about what happens if we take both coordinates and we make them infinitely big, both of them, where we're covering all of our squared, right? Any point that we consider, eventually we're going to cover. So the probability of being in that region where A and B become arbitrarily large is eventually 1. So when we take the limit, maybe I should have asked you so you would think about it. That probably would have been better. So sorry about that. But yeah, so the probability when we take A and B to infinity is going to be equal to 1. So maybe now I will ask you a question. Imagine that you have 2 points, and that one is here and one is here. Remember, like this is A and B, or I don't know if I flip them, but it doesn't really matter. Can the CDF here be smaller than the CDF here? Think about it for a moment. The answer is no, because the probability that you are here has to be smaller than the probability that you are here. Because if you are here, you are also in here. Okay, so one of the events is in the other event. So that means that just like in the 1D case, when we increase the arguments of the joint CDF, it's non-decreasing. You cannot make it decrease by increasing either of the arguments. Okay, this is what I'm saying here. Okay, can we have that this is, the value of the CDF at A1, B1 is greater than the value of the CDF at A2, B2 if A2 is greater than A1 and B2 is greater than B1? No, this cannot happen. Okay, because of the meaning of the CDF as a probability. Okay, so another question. Imagine that I have a point so I want to know the probability that I'm in a certain rectangle. So this is going to be A again, A1, A2, B1, B2. Okay, so I want to know the probability that I am in this rectangle here, and I want to express that probability in terms of the joint CDF. Why do I want to do that? Because then I can express the probability of the 2D random vector being in any union of rectangles in the same way. So this will mean that the joint CDF actually gives you all the information you need about the random vector. You can forget about the underlying probability space. Okay, so think about it for a moment. And the idea is that if you look at the CDF at this point, the CDF at this point gives you the probability that you are here. So that's pretty useful. You're on your way. So maybe you can take that and subtract this guy here. So you're taking away this part. Okay? If you subtract that part, what you end up, so if we take this and subtract this, we end up with this part, right? So now we're annoyed by having that, so maybe let's subtract it. So we would subtract this guy. That's great. If we do that, we actually get this, but you might realize that you have subtracted this twice. So then we should add this guy back again. And that's exactly how we do it. This is the upper right corner. We subtract these two other corners, and then we have to add the lower left corner. And all of those have expressions in terms of the joint CDF. The good news, you can express the probability of ending up in any rectangle, and by the same argument, ending up in any hyper-rectangle if you have d random variables or a random vector of dimension d, you can express it with the joint CDF. The bad news is that it's very cumbersome. It's even worse than in 1D. It's really annoying. We are not going to want to do this for very complicated sets. So usually we don't do this, although we could. The joint CDF has all the information that you need from the random vector. Instead, what do? We look for local information, because again, the CDF is really non-local. I mean, realize that when I was making this argument, every time I consider the joint CDF at a certain point, it tells you the probability of all of this. You might want to know what is happening at a particular point. And if you remember, that's exactly what the density gives you. We define the density as, in 1D, as the probability that the random variable is in a particular interval divided by the length of that interval. And that's what gives us a density. So in the end, it was a derivative. We're going to do exactly the same thing in multiple dimensions, except that in 2D, for example, we're going to consider the probability that the random variable is in a square. And that actually looks like a square. I'm quite proud of myself. And a square with sides equals to epsilon, so that it has area epsilon squared. And we're going to divide the probability that we end up in the square by the surface, and that's going to give us a density. This is kind of similar like if you have a sheet of metal that is really, really thin, and you say, okay, the mass is obtained by considering the density, the 2D density, and then integrating it over 2D. This is exactly how we are defining probability densities for 2D. In 3D, it would be the usual density that we consider, where we're dividing by a volume. Okay, but let's focus on 2D for a moment. Okay, so this is the probability that we're in a square touching the point AB. The square has a surface that has area epsilon squared, and we're dividing by epsilon squared. Now we apply our formula with the CDF for the probability of being within the square. And now what we do is we group, and we basically group the terms here so that we divide by one of the epsilons and take the limits, and we just obtain derivatives. Okay, this is more calculus. It's not super interesting. It's just going to show us that essentially we differentiate the joint CDF in one direction. That gives us a derivative with respect to A. And then we differentiate it in the other direction, gives us the derivative with respect to B. So it's not very surprising. This is multivariate calculus essentially. If you want the density of a quantity that is differentiable in 2D, you differentiate with respect to A and with respect to B. Okay. And this is just comes from the definition of partial derivatives. The important thing is to gain a bit of an intuition about this. So now, when you think of the density of a 2D quantity, the density tells you what's the probability locally of being in a small square if you divide by the area of that square. So if we see places with very high density, so here that would be essentially here between 2 and 4, between 0 and 4 and 0 and 4, okay, because basically this is the probability that you are there. Okay, this is very important. So here we have two entries of a random vector. The probability that you are there is essentially the volume under the density. We'll see in a moment. It's just the same idea as when we defined the density in 1D and then we were looking at areas underneath. Okay, so basically what I wanted to show here is that where you have higher density, that means that you have more probability of being there, but you have to remember that the probability is normalized by the area of that region, if you're talking about 2D. When we're talking about multiple dimensions, I can't even draw this, but the idea is kind of the same. Okay, like you're in a certain area of this d-dimensional space, the probability of being in a hypercube divided by the hypervolume. I don't know if hypervolume is a name, but the volume of the hypercube. When the hypercube becomes really, really small, that's the density of the random vector. Okay, and because of this proof that we showed here, you can express the density as the derivative with respect to both coordinates in the case of 2D of the joint CDF, or with respect to every coordinate if you're in D dimensions. And this is usually how we think about it. You have your joint CDF, which is a probability, you differentiate, and that's how you obtain the density. Okay, so now what are we going to do with the density? Well, you can use it to compute probabilities in the same way that you used the 1D density to compute probabilities. So because of its definition in terms of the joint CDF, and we're not going to repeat that here, but essentially the definition as the derivative of the joint CDF implies that when we want the probability of being in any Borel set, we just need to integrate over the Borel set exactly like in 1D. In multiple dimensions, the same thing. You want the probability of the random vector being in a Borel set, you just integrate the density, which means that you compute the volume under this density surface that we saw. Okay, always integrating over the set of interest. We're going to see an example in a moment. So what happens if you integrate over everything? You have a 2D function and you integrate its density over everything. That's going to be the probability of being anywhere, and the probability of being anywhere is always equal to 1. Okay, so joint densities, when you integrate them over all of the dimensions, they always integrate to 1. Same thing for D dimensions. Okay, and now let me ask you, are they non-negative? And the answer is yes. And now let me ask you why. And it's not like the joint CDF, right? This is not a probability, but it's very related to the joint CDF. It's because the joint CDF cannot be decreasing in any of its coordinates. Then the joint PDF essentially is taking derivatives with respect to all those coordinates. None of them can be negative because the joint CDF does not decrease. So then the joint PDF, the joint density, ends up being non-negative. So it's tricky. It's due to the fact that the joint CDF is actually not decreasing. Here I've written it down for 2 dimensions. Same thing when you're in D dimensions. It turns out, okay, and this is, a speech that I've given you many times by now. Like we started, with what if you have like a PMF that is non-negative adds up to 1? Is there always an underlying probability space? The answer is always yes, 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 yes. Here, if you have a joint PDF that is non-negative and integrates to 1, you can build an underlying probability space. You will never do it, but you can, where basically your sample space is going to be RD, like this D real lines, the D-dimensional space, and then you're going to take Borel sets as your collection, and the probability measure is going to be given by the density. Again, this is just in case, some mathematician friend of yours says, okay, but where's the underlying probability space? You could construct it once you have a non-negative joint density that integrates to 1, but we never do it. Okay, so let's take a look at an example. Okay, in this example, there's a biologist that is studying an otter who happens to live in this lake, which has this very convenient shape when we do integrals. And the first question is, okay, like if the otter can only be here and it has uniform probability of being anywhere there, what's a reasonable definition for the joint PDF? Well, a reasonable definition is that, please think about it for a moment. And when I ask you questions, I really encourage you to just stop the video and think a little bit about them. What's the density going to be outside here? The density is going to be 0 because the otter cannot be outside here. And if you integrate over anything here, you want to get 0 always. So here, the density should be 0. Now, what should the density be inside this triangle? Well, it should be constant because we're saying that the otter is uniformly distributed, whatever that means, over this lake. And a reasonable, well, I said whatever that means, but a reasonable definition of that is that the density of probability is constant, which means that if I integrate a small square here and a small square here, I'm going to get the same probability as long as the squares have the same area. Okay, so what should be the constant, right? So I'm going to have that this guy here is equal to the constant, but what should the constant be? Well, this should integrate, all of this should integrate to 1, so this is a valid joint PDF. That's going to be the area of the triangle times this constant. The area of the triangle is 1/2, you look at it, so the constant should be equal to 2. Okay, so that's going to be the joint PDF of the otter in the lake. Now imagine that we want the probability that the otter is between 0.6, so above here, and below 0.2, so here. So imagine that we want to know the probability that the otter is here. We can use the joint PDF to compute that probability by just integrating. So it's going to be essentially the area of that shape that I just drew multiplied by the constant c. Okay, I always like to write these things in terms of integrals. We're integrating over this set intersection this other set, intersection being inside the lake, because outside of the lake the density is 0. Inside the density is equal to 2. This is the same as integrating b from 0 to 0.2, so we're integrating b like that. And at the same time, we're also integrating a. And with a, we have to be careful, right? Because we're integrating from 0.6 upwards, but we're going to hit this line here. And that line here is 1 minus b. This is why here we're integrating only up until 1 minus b. Okay? So that's the idea. We're integrating first. When you're doing 2D integrals, first you're integrating one direction from 0 to 0.2, and then you have to be careful that you don't end up including this part outside. And that's why we're ending at 1 minus b. Again, I encourage you to try to do this on your own. That's really the way you can see whether you remember your multivariate calculus. Not that we need very complicated multivariate calculus, but just a bit. That's a way to see if you remember. Okay, and when you do this, you do the integrals, and you get that the probability is 0.12. Okay, and that's usually how we compute probabilities of a random vector being somewhere. We tend to integrate the density much easier than integrating the joint CDF. Okay, so as usual, we've gotten a bit carried away with the math. We've been talking about the mathematical characterization in terms of probability spaces. We have defined the joint CDF. We have defined the density. Where is the data? What do I do? I have a bunch of data. What do I do with them? Right? And it's really important to try to connect all those ideas to that. Well, essentially what we do is we estimate a joint PDF. That's usually what we do with multivariate data like that. If we want to characterize the density, if we want to estimate a PDF from data, in order for it to be a valid PDF, all we need is for it to be non-negative and integrate to 1. That's it. Of course, the question remains whether it actually captures the information that we want it to capture, and that's, that's much tougher because we always have limited data and so on. But if we come up with a function that is non-negative and integrates to 1, it is at least a valid density. We cannot use empirical probabilities in the case of continuous quantities because the probability of each data point is 0. This is something that we already discussed when we were considering a single continuous quantity. Instead, what we tend to do is we estimate the density directly, and we saw two ways of doing that: the histogram and kernel density estimation. Kernel density estimation extends in a more natural way to multiple dimensions, so we're going to focus on that. Although you could also have multidimensional extensions of the histogram, and the ideas would be very similar. So remember that in kernel density estimation, essentially what we said is, we have, I'll just go to the picture actually, because the equations, if anything, will just confuse you. The idea is very simple. We have 3 points, x1, x2, and x3, and we say, okay, I'm going to build a density by taking shifted copies of this kernel function that integrates to 1, and I'm going to multiply it by 1 over the number of points. Okay, I'm going to just put shifted copies centered at those points, and then their sum is going to give me the density. Which is nice because basically what you're saying is, if you're close to points where there's a lot of data, then the density should be high. If you were not close to any points where there's data, like here, for example, the density should be very low. It's also nice because each of these shifted copies integrate to 1. If you multiply it by 1 over n, then this ensures automatically that everything is going to integrate to 1. Feel free to go review. We already covered kernel density estimation in 1D in detail, but these were the main ideas. In multiple dimensions, the idea is exactly the same. So, okay, let's say that we have 3 points. Now, of course, I cannot put like a 1D blob on top of the points, but you know what? I'm going to put a 2D blob. Actually, it's 3D, right? Because the density comes up. So I'm going to put a blob here, because this is the location of one of the data points, another blob on top of this other location, and another blob here. And each of these blobs have a volume that is equal to 1 underneath them, and I multiply them, in this case, by 1 over 3, so that when I add them all up, the volume underneath is equal to 1. And that's it. That's kernel density estimation. This plot looks very cool, at least I think it looks very cool, but usually it's very difficult to see what's going on when you look at things in 3D, because you would have to look at them from, a couple of angles. So usually what we do is we ask ourselves, what are the contour lines of this mountain that is coming up, just like when you look at a map of a mountain and you see the altitude in different contour lines. And that's how we usually describe the kernel density estimate. Okay, so here you see the density in a very fancy 3D way. Usually, at least I like to look at things like this. So here we see that the density here is equal to 0.03, 0.04, 0.07. Okay, so we see actually that there's a peak here, and it's often cleaner to look at it like that. Of course, there's a bit of a decision where to put the contour lines and so on. You could also do heat maps. That's another good possibility, in fact. Okay, so that's multidimensional KDE. Basically, you have endpoints. You put shifted copies of a kernel function on top of each of the points. And this is not only for 2D. You can also do it in D dimensions. It will be more difficult to visualize, but you will get a density in the dimensions. And you need to ensure that the kernel integrates to 1, then you're multiplying it by 1 over n, so everything actually integrates to 1. And you have this parameter h that governs how fat the kernel is. And that's a parameter that you can tweak depending on the number of data that you have, according to different rules or different procedures, and it will actually affect how your density estimate looks like. And we're going to see in a moment. So let's take a look at an example where we have temperature in Versailles, Kentucky. I just thought it was, the name is funny. And Manhattan, Kansas. There happen to be 2 weather stations there, so there's plenty of data. And, I kind of like the names. And these are basically points of temperatures in Versailles, in Kansas and Kentucky in 2015. Just to make clear, basically, if we see a point here, that means that at some point it was 20 degrees in Kansas and close to 0 degrees in Kentucky. So at that point, actually, it was very cold in Kentucky, not so cold in Kansas. All of this is Celsius. I'm from Spain. I'm just more used to it. Like I can't wrap my head around Fahrenheit. In general, we see that when the temperature is high in Manhattan, it's also high in Kansas. But it's the distribution is actually kind of interesting because there are more points concentrated here, whereas there's many less points concentrated here. So when it's very cold, there seems to be more variation when it's cold as opposed to when there is warm. That we can just see by looking at this scatter plot. Okay, so now we're going to apply kernel density estimation with different bandwidths for the kernel. If we make the bandwidth very, very small, we end up with a very noisy estimate that kind of overfits certain structures, right? Like, so do we really think that the density here is higher than around just because we had a bunch of points that are there? I'm not a climatologist, but probably not, right? When we make the bandwidth a bit bigger, then we smooth out that noise, which is a good idea because we're not overfitting the training data that we're using to compute the density. But we don't want to smooth too much because we might lose some structure. So here maybe we're making things seem a bit more, a bit more regular than they should be. And again, these are contour lines that tells us that basically there's a little mountain coming up here, coming up here. Okay, so what have we learned? We have learned how to describe the joint distribution of continuous quantities using multiple random variables defined on the same probability space, and we saw that everything works out as long as the individual continuous random variables are well defined. Then we introduced the joint CDF and joint PDF that allow us to manipulate the random variables without having to refer to this underlying probability space. And finally, we saw how to estimate the joint PDF from data. Thank you very much.